Hello, thank you very much for donating some of your valuable time to listen to our presentation today. Following a brief introduction to Silicon Creations and our main product lines, I'll explain how our PLLs achieve fractional multiplication without compromising the quality of the output clock using the built-in jitter compensation. This enables our PLL to be used in a huge variety of applications, making it almost a one-size-fits-all PLL. The best part is that this PLL is available today in Samsung's advanced FinFET process nodes, and following this theoretical overview, I'm going to tell you about a few of the diverse clocking applications that are enabled by adding synthesizable RTL to our Fractional-N PLL. By the end of this presentation, I'm sure that you will agree that this PLL will enable you to reduce your SoC project risk. Silicon Creations has been providing clocking IPs since 2006, and we've been growing particularly quickly in the past few years. We have development centers in Atlanta in the USA and in Krakow in Poland, and have developed mass production IPs in a wide variety of process nodes. We're ready to deliver some of our IPs already in Samsung's FinFET process nodes down to 4 nanometers. Our priority is to help our customers get to market quickly, and our support has been recognized with multiple awards. PLLs, such as our widely programmable general-purpose fractional synthesizer, are used in a wide variety of markets and applications. The wide programming range of our Fractional-N PLL means a single design can generate most of the clocks advanced SoCs require, and most of the chips using these PLLs have multiple instances. The resulting production volumes have led to an extremely robust circuit architecture. We've also leveraged this high-volume design to make PLL variants that are optimized for low jitter and extremely low power, and some of our specialized PLL variants will be introduced to you in this presentation. Now let's look at the different kinds of jitter that all PLLs generate and how our fractional PLL works. This slide shows the main kinds of jitter which are important to understand when designing systems with clocks. The picture shows what you might see if you trigger an oscilloscope on the rising edge of a clock. Many oscilloscopes allow you to generate a histogram of the crossing points for the rising edge after this trigger. If you look at the histogram of the crossing times for the first rising edge, you're measuring the period jitter. If you look at a histogram for the second rising edge, you are looking at what's called the two-cycle jitter, which is the same as the calculated difference between the first and second periods. This is also called the cycle-to-cycle jitter. If only random jitter is present in the clock, you will see histograms with nice bell curves, which are technically Gaussian curves. The sigma, or RMS value, of the cycle-to-cycle jitter will be a factor of square root of 2 larger than the RMS period jitter. This period jitter is also known as short-term jitter, and this is important for the timing margin in digital circuits. If we keep increasing the oscilloscope delay until a time that is comfortably more than 1 over the bandwidth of the PLL, we will measure what is called the long-term jitter. This jitter determines the performance of data converters and SerDes data communications. There is a very important contributor to jitter in PLLs, which is not shown in this diagram. In most SoCs, power supply noise will modulate the delay of buffers and logic cells, and this adds what's called deterministic jitter. In most chips, this added jitter is much larger than the period jitter, and is also larger than other sources of deterministic jitter like unfiltered reference clock jitter and mismatch in the PLL circuit. When chip designers use our PLLs, we provide a lot of guidance on how to estimate the elements of this deterministic jitter and safely design chips that can meet their requirements. Now let's jump into an explanation of what PLLs do and how ours is different. This is a block diagram of a conventional integer PLL. It's called an integer PLL because the output clock is equal to the input clock multiplied by the ratio of 2 integers. An important limitation of this kind of PLL is the smallest step that is possible in the output clock, with typical limitations on divider values, input clock rates, and VCO designs. This is typically around 2% or even larger, and in many SoCs, this makes it impossible to create all desired frequencies without either multiple crystal reference frequencies or placing multiple PLLs in series. Both of these options cost power and increase system cost. In the PLL that we're introducing in this talk, we overcome these unpleasant limitations by adding a logic circuit to the classical PLL. This functional block is known as a delta sigma modulator, and it constantly changes the feedback divider value so that the output clock can be changed in truly tiny increments. In our Fractional-N PLL, a 36-bit modulator with 24 fractional bits and 12 integer bits means the smallest steps in the output clock have been reduced from 2% to less than 0.003 ppm. This means that with any typical crystal reference frequency, the PLL can generate any output clock from a few megahertz to several gigahertz with a precision better than that of the crystal itself. This graph illustrates how the delta sigma modulator works by showing two ways the feedback divider can be modulated to create an effective feedback divider value of 10 1/4. In the top curve, we see the most direct or intuitive approach. Divide 3 times by 10 and then once by 11 and repeat this continuously. This approach is simple, but for many fractional bits will create low frequency disturbances in the feedback divider value. Disturbances in the output clock can only be reduced with very large loop filters. Modern Fractional-N PLLs get around this by mixing in more values and increasing the frequency of the changes of the feedback divider value. The lower sequence achieves the same average feedback divide value, but the deviations can be smoothed out with a much smaller loop filter. Nevertheless, it's clear that the desired output clock quality will determine how large the loop filter needs to be. In our Fractional-N PLL, we add yet another circuit. We split the current source in the current mode VCO into multiple elements, which was necessary anyway in FinFET, to turn it into a DAC and continuously change the DAC value so that the VCO current is modulated with the inverse of the impulse errors introduced by changing the feedback divider. This measurement of the phase noise output from our Fractional-N PLL shows the benefit in practice. When we enable the DAC, the output jitter is improved by more than 20 dBs, or a factor of 10. This is an extremely good result for a ring PLL, and in this example, the 5 picoseconds of long-term jitter is the lowest for any general-purpose Fractional-N PLL from IP providers. Okay, now that we've looked at how our Fractional-N PLL works and the special circuits we include in it, let's look at how this flexible PLL can be used. The most common use for our Fractional-N PLL is for dynamic frequency scaling. We load the integer and fractional values into our delta sigma modulator on every divided feedback clock. This means that the PLL target output frequency can be changed rapidly and predictably. Our Verilog model enables you to watch the dynamic response of the PLL to its programming, including startup behavior, to ensure that your system does not include any implementation errors. Another item illustrated on this slide is the power supply domains included in the PLL. Powering the VCO from the I/O supply provides very good supply rejection and enables all PLLs to share a single supply. We separate the core supply circuits to those clocked at the reference clock rate and those clocked at the VCO rate. In most SoCs, these core supplies can be shared with other core supplies on the chip. Our customers appreciate the guidance they receive from our designers because this usually allows them to reduce the number of supply and ESD domains on their chips. This can lead to substantial cost savings. Capitalizing on this ability to continuously change the feedback divider target, our SSMod modulator is delivered as synthesizable RTL. When added to any of our Fractional-N PLLs, a spread spectrum clock generator, or SSCG, is created. The modulator is only about 4K gates synthesized, adding negligible area to the PLL. The modulation frequency, output spectrum shape, and extent are all exactly controlled and will be exactly the same in every production device. You can see a measurement of the output frequency spectrum on the right demonstrating the flexibility of this SSCG. We also provide a digital loop filter, DPLL, that can be added to any of our Fractional-N PLLs. The DPLL calculates the right feedback divider values needed to multiply a fixed reference frequency up to exactly match the average of the DPLL input frequency. The resulting dual loop PLL is known as a Jitter Cleaner PLL or Jitter Attenuated PLL because the effective bandwidth can be programmed to extremely small values. We've measured below 1 Hz in our lab. The output jitter is determined by the quality of the Fractional-N PLL, which is excellent in our case, and the stable reference source. We've measured below 1 picosecond RMS of integrated jitter. With less than 20K gates, the DPLL adds very little area to the Fractional-N PLL. For example, that's less than 0.013 square millimeters in 40 nanometers and much less in FinFET. The Jitter Cleaner PLL is fully integrated and can replace external chips costing upwards of $8. Applications for this Jitter Cleaner include optical communications, despreading of recovered clocks in video systems, and PLLs to multiply very, very low input clocks. The measurement on the right shows an input spread spectrum clock. The effective jitter of this clock is over 2000 picoseconds. The output is a despread clock, which has a frequency of the average of the input clock and integrated jitter of around 1.5 picoseconds RMS. Because our Fractional-N PLL behaves well and predictably when the output frequency is changed, we can change the output up or down by a very small amount for a small amount of time. The result is that following this change, the output will be at the same frequency, but the output phase will have been shifted by a programmable amount. One of our engineers measured how well this circuit works in the paper referred to here. You can see from the graph on the right that the output phase step tracks the calculated value down below 0.01 degrees. This is an extremely small phase step, and some of our customers have used this capability in very interesting ways. One of the uses we enable is to precisely align 2 clocks at any location on a chip. The phase stepper is combined with an early-late detector that is placed exactly where the clocks need to be aligned. These circuits are digital and can be synthesized together with the rest of the core logic fabric. Aligning clocks at the end of the clock tree enables circuits to run faster or latency of data transfers between clock domains to be reduced or even eliminated. We have also added a state machine and some counters to these phase shift and early-late detector blocks. We call the resulting circuit a Jitter Monitor. This capability is useful in reducing system test costs and can work as a continuous monitor to alert users when the performance of a system is degrading due to particle faults or some other disturbance. To save die area and cost, we assume the state machine will be controlled by software, either in the production tester or in an embedded processor. On the lower right, you can see an example measurement. The blue line is the cumulative density function, which has been used to calculate the jitter histogram with a precision equal to that achievable with expensive test equipment. Despite the very wide programming range of our Fractional-N PLL and the great flexibility that the add-on logic circuits provide, this PLL doesn't quite cover all clock applications. The next few slides introduce some of the specialized PLLs we've developed using some of the same core analog circuits. In many small chips, the clock quality does not need to be that good. For these chips, we've removed the modulator, made the loop filter much smaller, and used only core transistors to create a very small integer-only PLL that uses only the core supply. These PLLs are truly tiny and very easy to use, and in very low cost. These PLLs are truly tiny and very easy to use, and in very low cost chips are just what's needed. Similar to our LA int PLLs, our DSKU PLLs are designed to clean up a reference clock, multiply it by a binary number, and generate an output with really good duty cycle for source synchronous interfaces like DDR. Self-calibration of the offsets caused by device mismatch allows this PLL to be used to align the end of a clock tree, like the input of the last flip-flop in a serializer, with the reference input. The last specialized PLL variant we're introducing is what we call an IoT PLL. This PLL has a larger loop filter so that it can be used with a 32.768 kHz real-time clock as a reference. In some of these IoT PLLs, we include multiple VCOs, one designed to use just a few microamps so that the PLL can clock always-on audio codecs or system state control logic. A startup frequency calibration circuit ensures the PLL can generate a useful output clock within 10 cycles of a cold start and within 3 cycles or less than 100 microseconds on warm starts. This capability reduces system energy consumption in chips that spend most of their time asleep, and that's why we've called it the IoT PLL. This brings us to the end of our presentation. Thank you once again for donating us your attention. In this presentation, we first talked about how Silicon Creations has been providing clocking solutions for 1.5 decades, and how our customers use our IPs to reduce their go-to-market risk. The mainstay of our clocking IP is our Fractional-N PLL, and we explained how this PLL is different from other PLLs. This PLL is available today in most of Samsung's advanced processors, and we've collaborated with Samsung Foundry to introduce this PLL in 5 nanometers and in 4 nanometer FinFET processors. We expect test chips in 4 nanometer LPP in our lab soon. We then talked about how this flexible PLL can directly generate clocks for dynamic frequency scaling and spread spectrum modulation. And we introduced logic circuits that can be added to this PLL to solve a wide variety of system clock challenges, and even enable SoCs to self-measure the quality of the clocks generated on-chip, which can increase system safety and reduce test costs. Although this Fractional-N PLL is incredibly flexible, it's not quite a one-size-fits-all PLL, and we introduced 3 PLLs we provide that share much of the core circuit topology with the Fractional-N PLL. If you would like to learn more about our PLL or other clocking solutions from us, please visit our booth or contact our sales team. Once again, thank you for your attention.